Hi again. In this section, we're going to be working with some examples in hexadecimal and octal numbers. So first, let's see how we do hexadecimal to decimal conversion. Remember, we can convert a hexadecimal number to a decimal using power of 16. Okay? So for instance, if we have these two numbers, 356 in base 16 and 2AF base 16, to convert, all we need to do is what? Well, we need to use all our knowledge and represent this as what? This is essentially, we can do positional notation and we can do the polynomial representation, and then just give the values here of the coefficients in the polynomial depending on the position, and the power will be, or the radix will be in this case 16. So 356 then is equivalent to 3 times 16 to the second, because remember, this is position 0, position 1, and this is position 2, meaning power 0, power 1, power 2. The radix in this case is 16. Well, all we need to do is just plug in each one of the values, get the product of the coefficient times the respective power, and then add them up, just as we did with the decimal representation. In the other case, 2AF, exactly the same thing. All we need to do is remember that A is what? A is 10. So we're going to be substituting the value of A here by 10, and F is going to be 15. Okay? Same thing. It doesn't matter that we have a letter or we have a number. Remember, each one of the hexadecimal numbers has their equivalent number in decimal. That's the one that we're going to be using for the calculation. Okay, so this is simply just doing all the calculations, all the operations. Okay, now we want to bring now from decimal to hexadecimal. How do we do that? How do we convert from decimal to radix or base? Well, we've seen the two different methods. One is the successive division with reminders, and the other one is the subtraction method. In this case, remember, we haven't seen any of the subtraction method, therefore we will keep working with the successive division. Okay, so since we're moving from decimal to hexadecimal, what would be the radix that we want to be using? We're going to be using 16 as the radix. So in other words, if you have this number, 432, all we need to do is start dividing 432 by 16, okay? And see what the remainder is. The remainder should be a number between 0 and 15 for any of those limits, from 0 to 15. So 16 cannot be a remainder, remember. So the first division is 423 by 16 is 26, but we have a remainder of 7. Okay, remember, same as we did with the binary, the first digit that comes in this calculation is going to be 1, the least significant of the digits. Okay, the second round, the second lap, yes, is 26. Now it's our quotient. We want to divide that by 16. Okay, and 26 divided by 16 is 1. The remainder is 10, and 10 is, remember, A. And now this is our quotient. Remember, here's how we stop it. This is the last remainder. We know there's no possible division, so we assume the quotient we let the 0, but the remainder, that's what we're looking for, is going to be 1. Okay, because it's 1 divided by 16. Let's see the 214. Okay, we proceed exactly the same thing. First, we divide by 16, and the quotient is 13, and the remainder is going to be 6. Then this quotient, which is 13, it will be, we attempt to divide it by 16, but you know, this would be the last step, and that corresponds to the remainder that, or the quotient in this case is going to be less than the radix, so we assume that this is the last remainder. In 13 is D. So in this case, we remember this is the least significant of the numbers, in this case of the 432. This is the one in the middle, and this is the most significant. So whenever we read this number, it's going to be 187. And here, there will be D6, okay, in hexadecimal. Octal numbers. Well, the same thing that as we did with the hexadecimal. Remember, we group 4 bits, and these 4 bits are treated as a separate digit, right? This is essentially the hexadecimal, and because we're using power of 2 also, a number is going to be from 0 to 15, we can simply, if you have any big number, a big binary number, then all you need to do is divide into group of 4, starting from the right towards the left, you group by 4 of those bits. And this is the way, as we're going to see, how we convert from binary to hexadecimal. All right. So what we did, the treatment we did with the hexadecimal is similar to the one we want to be using for the octal. And octal, we have 8 different symbols, and those symbols will correspond to all possible digits or values between 0 and the radix minus 1. R minus 1, in this case R is 8, R minus 1 is going to be 7. So we can display, we can use all digits between 0 and 7. All right. So in this case, we will be using numbers in power of 8, because that's the radix we're using. 8 to the 0 is going to be 1, of course. 8 to the first is 8. 8 to the second is 64. 8 to the third is 512. And here, here are the numbers. All possible numbers in octal: 0, 1, 2, 3, 4, 5, 6, and 7. Those are all possible digits. I use 4 bits, but remember, for octal, all we need is 3 bits, because we represent from 0 to 7 with 3 bits. 7 is 1, 1, 1. Therefore, all I need is 3 bits. Just an aside, octal numbers were very used when computers had word size of 12 bits. And then we group by 4 octal numbers, each one of 3 bits, and make it 3 octal reading of 4 octal numbers, okay, from memory, etc., etc. Same as we did with hexadecimal. Let's see how we perform. Let me give this in case that we are displaying other numbers with 4 bits using octal. Okay, remember that starting here with the 7, for which we only need 3 bits, then the next one will be adding 1 in the leftmost of the bits, but now it comes with a 0 and 1. Okay, this is assumed to be 1 octal, and this is 0 octals we have here. So 1 0, this would be 1 1, and so on and so forth. All right, let's see how we convert then octal to decimal. If we want to convert to decimal, remember all we need to do is just have each one of the digits, plug it into the either the positional notation or the polynomial, and just plug it in and make the calculation. This is straightforward. Okay, so 415 is going to be 4 times 8 to the second plus 1 times 8 to the first plus 5 times 8 to the 0. And this is all we need to convert. 101 octal, if you want to know the decimal, is simply plugging in the coefficients 101 into the polynomial. Okay? Now, from decimal to octal, okay, we apply what? Well, apply what we learned about the two methods. Now we're going to be using only one, which is the successive division. In this case, is the radix is 8. Therefore, we need to divide by 8. Okay? And read the remainder. That's exactly the same thing. For instance, the number 498 in decimal. We start dividing 498 by 8. The quotient is 62 with a remainder of 2. Then this 62 is divided by 8. The quotient is 7 and the remainder is 6. Then we divide the 7 by 8 and then that stops because the quotient in this case is smaller than the radix. So we assume that the quotient here is going to be 0 and the remainder is going to be 7. So here's the number, 762. Same as before. The first number that we discover with this process is the least significant. It's the A0 in the polynomial. Then we discover the A1, which is the second from the right. Then we discover the most significant. In this case, it's the 7. If we use another example, it's the 512, and we divide that by 863 with a remainder of 7. Then we divide the 63 by 8 with a quotient of 7 and remainder of 7, right? And then we use this quotient, 7 divided by 8, and the remainder is going to be 7. So the 511 is 777 in octal. All right. Okay, I'm going to stop here. This is very short because the next topic I'm going to cover is the other method, which is the subtraction method. Okay,